Okay, so today for recitation, we will just practice more with cylindrical and spherical coordinates. So let's take a look. So just quickly review everything. Cylindrical, you're really just converting x and y into polar. You're not really doing anything with z. And so just like polar, you have your extra r. I sort of explained where that came from yesterday in the optional material, if you want to take a look at that. But again, just r is distance to the z-axis, and it's a distance, so we never let r go negative. And yeah, that's about it for cylindrical coordinates. So basically, anytime where your shadow d or your projection d of your solid region E is good for polar, then you're probably going to want to think about cylindrical coordinates. So spherical is when you have a sphere involved somehow in your region. And so for spherical, remember we have our two angles, theta and phi. Theta is the same theta. Phi is down from the positive z-axis. So this is phi equals 0. Phi equals pi over 4. Phi equals pi over 2. So you could really think of phi as being like latitude, except 0 starts at the North Pole, whereas latitude 0 is the equator. But anyway, here are the equations for x, y, and z. You probably want to memorize those as soon as possible. You can figure it out from triangles. Remember, the triangles that we have are r, z, phi, rho, and x, y, r, theta. And so using SOHCAHTOA, right triangle trig, you can figure out all those relationships for x, y, and z in terms of rho, theta, and phi. And then again, when you're doing integrals, it's very important that you include the appropriate factor on dv, which for spherical coordinates is rho squared sine phi. Again, I sort of showed you yesterday where that came from. It was the generalization of substitution into multiple integrals. But anyway, the other big thing was theta between 0, sorry, not theta, phi between 0 and pi. And so phi between 0 and pi actually does two things for us. First of all, it keeps that coefficient on dv positive, which we want. The formula I showed you yesterday, technically there should be an absolute value around that, but if we're careful and never let phi go outside of that range, 0 to pi, then we're good. And I guess the other thing that phi between 0 and pi does for us is it helps to prevent us from double counting points. So for example, if you do 0 to 2 pi, 0 to 2 pi for both theta and phi, you're going to count every point twice. And it's basically similar to how if you look up and understand what's going on with latitude and longitude, the fact that longitude, we have 360 degrees as the width, and latitude, it's only 180 degrees. So for example, if you go latitude 95 degrees north, you've gone 5 degrees past the North Pole. You shouldn't do that. You should never go past the North Pole when you're doing latitude. You should instead go 85 degrees. So you go 5 degrees less than straight up at the opposite longitude value. So this would be like longitude, let's say 0, 95 latitude north. You go past the North Pole by 5 degrees, whereas if you go 180 degrees longitude, so for example, prime meridian, 95 degrees north, you could get there by going, oh God, is it the international date line that's opposite the prime meridian? I should know more about geography. But if you go the opposite longitude, 85 degrees north, you'll get to the same spot. So anyway, for those two reasons, we're very, very careful to keep phi between 0 and pi. But yeah, let's just do one more example, practice both on the same region, sort of like what we were doing yesterday. So setup, usually both cylindrical and spherical, triple integral. I don't even tell you the integrand f, but we're above a cone and below a plane. So I don't think we looked at something quite like this, but we have this cone which you could think of, pre-calc style graphical transformations, taking our standard cone, z is square root x squared plus y squared, and dividing z by root 3, you're sort of vertically compressing it. Vertically, which means as far as the z-axis goes. So it's actually going to make this cone wider. So I don't know. I'll try to draw it a little bit like that. So we have our wider cone, and then we have our plane z equals 4, which of course is horizontal. So we have something like this. And so, okay, you think about it. What's going on here? Our solid region E is above the cone, below the plane, so it's there. And so as far as cylindrical coordinates goes, again, remember, cylindrical, you're still doing bottom and top surfaces. So z equals this cone equation, so 1 over root 3 times square root x squared plus y squared, that's your bottom surface. Whereas, of course, z equals 4, this plane, is our top surface. So as far as cylindrical coordinates goes, we convert any x's and y's that we see into polars. So you're going to have r over root 3 as your lower bound for z. And then your upper bound for z is going to be 4. And then, yeah, I didn't really tell you what the integrand was, so don't worry about that. But don't forget your extra r that comes in with dv. And then from there, I guess all we have to do is figure out our r and theta bounds. So pretty clearly, we're going all the way around the z-axis. So theta is going to go 0 to 2 pi. And then for r, we need to figure out when r over root 3 equals square root 4. So we're intersecting the cone and the plane. And so without too much trouble, we see that r should go from 0 to 4 root 3. So r is the radius of this shadow. The shadow I'm drawing is the orange disk in the xy plane. Okay, so that's our cylindrical bounds. Let's try it spherical. And so you hopefully, if you paid attention yesterday, we had the sentence no, or I guess it's not even a sentence, but whatever. Our motto will be no sphere, no spherical. So look carefully at this region here, this cone. We don't have any sphere anywhere. So it turns out spherical is not going to be the most fun. It's not going to be so bad. What did we do? This was sort of a piece of when we were looking at our paraboloid type region yesterday. So it's not as messy as that, but it is somewhat annoying because this plane isn't a sphere. The rho value at these points that I'm stopping at isn't always the same, right? This point right here, straight up, that's closer to the origin than this point is. So it's only when you're stopping at a sphere centered at the origin that your rho is stopping at the same value at all these different angles. But when you don't have a sphere, and that's what's special about spherical, that's when spherical is fantastic. But when you're stopping on not a sphere, but something like a plane, z equals 4, this is your outer surface. This has a slightly messier equation in spherical. So just go back to all our relationships here. The plane z equals 4, if you translate it into spherical coordinates, you get that rho cosine phi is 4, so rho is 4 secant phi. And so that's going to have to go on your upper bound, or on your inside. So your inner boundary is the origin no matter what. So rho starts at 0. Remember, rho is distance to origin. But then your upper bound for rho depends on phi. So we're going to stop at 4 secant phi. I have f, rho squared sine phi, and then yes, our rho bounds depend on phi, so we do have to be careful to put rho on the inside of phi. When the bounds are all numbers, doesn't matter which order you do, but when your rho bound depends on phi, make sure to put that on the inside. Otherwise, your answer won't be a number, which is a big no-no. But anyway, we have that. I guess our theta bounds, it's pretty easy to convince yourself. Yeah, again, it's going all the way around the z-axis. It's the same theta as cylindrical, so you're never going to have a different situation for theta between these two coordinate systems. And then finally, I guess we have to figure out our phi bounds. So our phi bounds are going to start at 0 because remember, phi equals 0 is straight up. And then it's going to stop at whatever angle this cone is. So remember, cones tell us information about phi. And so we have to figure out what this angle of the cone is. And so, again, you have to look back at the equation of the cone. It was 1 over root 3 square root of x squared plus y squared. Z we know is rho cosine phi. And then r, which is the square root of x squared plus y squared, again, is not a spherical coordinate, but it's sometimes helpful to remember that r is rho sine phi. And so again, I think it's good to know that. I mean, you could always use the x and y ideas. You could say that x, of course, is rho cosine squared theta sine squared phi plus rho squared sine squared theta sine squared phi. But then the idea is that you could factor out a rho squared sine squared phi and apply the Pythagorean theorem for theta to get the square root of rho squared sine squared phi. And based on our restriction for phi between 0 to pi, you get the absolute value of rho sine phi, which is just rho sine phi. So anyway, I think it's good to memorize this, but you could always figure it out from up here using the Pythagorean theorem. So anyway, that's our cone equation in spherical. So now you play around with this. You can manipulate this to root 3 is tan phi. So that's a special angle. It's pi over 3. So like I mentioned before, this cone is a little bit wider than the z equals root x squared plus y squared. So we get a bigger angle here. So anyway, that's that. And so, yeah, secant is not fun to have to deal with when you're anti-differentiating. I think a lot of people who do this in spherical are careless and think that the upper row bound is just a number. So really, keep going with, this is scary, probably a big mess, but go by what we said yesterday. No sphere, so no spherical. This is better. So just another little practice on setting them up both ways, knowing which one is better. Okay. So I think what I wanted to do next today is to just extend some ideas that we talked at the beginning of last week about. So I guess for 230, that would have been week 8. For 232, that would have been week 2, when we talked about odd symmetry and how that can give you some shortcuts for calculating certain double integrals. So today I want to emphasize that we can extend those ideas to the 3D situation too. So for example, if you have an integrand that's odd with respect to z, and you have symmetry over the xy plane of your region, then the triple integral of this odd function in z over this region E that's symmetric over the xy plane ends up being 0. So for example, intuitively, if I think about what's going on here, so with this, you can't really think about this as mass density, but you could think of, because mass density is never negative, but maybe you can think about this as some sort of charge density. So a charge, of course, is allowed to be negative. So anyway, let's say we have our symmetry over the xy plane, right? So when you flip the solid region E upside down, you get the same thing. Remember, with triple integrals, like all integrals, you're essentially doing some kind of like Riemann sum limit. And so intuitively, you can think of your sort of, what does an integral mean? You're like adding up all the values. Technically, so for a single integral, you're adding up values, but then scaling by the length of subintervals. With a triple integral, you're sort of adding up all the values and then multiplying by the volume of some little box. Excuse me. But anyway, if f is odd, then with respect to z, the idea is that f has opposite signs when you switch z to minus z, which switching z to minus z flips you over the xy plane. So if f has opposite signs there, when you add up those 2 points, it cancels itself out. And then these 2 points cancel each other out. So the fact that you have the odd symmetry in your integrand tells you that anytime you do something like this, they cancel each other out. The symmetry of the region tells you that every point on the upper half has a counterpart in the lower half at which f works opposite. So when you add up everything cancels itself out, and you get 0. So f has opposite signs, so these cancel, and so on and so forth. So if you think about that in terms of charge density, that can really give you some intuition about this. But if you're a little bit suspicious of this, if you were to set this up, so the symmetry in the region, so E symmetric over xy plane, if you were to go through and set this up, you would have minus u of xy as your bottom surface, and u of xy as your top surface. So yeah, the symmetry in the region tells you that the bottom and top surfaces, the z equation is basically just plus minus itself. And then you have f of x, y, z, dz, dA. And so remember the Calc 1 property that if you integrate an odd function over a symmetric interval, this is 0 by Calc 1. So you get the double integral of 0, which is 0. So intuitively, you can think about all these charges as canceling, or if you want to apply the Calc 1 property, it applies to the innermost step once you've done your bottom and top surfaces. Okay, and so again, I've drawn z straight up here as usual. So the xy plane, flipping over the xy plane, you're just flipping upside down right here. Okay, so as you might guess, what's so special about z? Can I look for symmetry in other variables? And the answer is yes. So if you have odd with respect to y, then you're looking for symmetry when you flip y to minus y, which is symmetry over the the xz plane for your solid region. And then finally, if your integrand is symmetric with respect to x, if it's odd with respect to x, so changing x to minus x is equivalent to multiplying the whole thing by -1, then you can do this. Okay, so sometimes you might get lucky and have an integrand that is odd with respect to something, but what I think happens more commonly is that the whole integrand isn't, but maybe one of the terms is. So for example, if you have the triple integral of f plus g, you could do it as the triple integral of f plus the triple integral of g, and maybe f does have some odd symmetry, and so that piece you can work out to be 0. So the fact that it's well behaved over addition allows you to split terms up. And so if you combine this with the fact that there's some triple integrals we immediately know because they correspond to known volumes, and then again, finally, if you have numbers as all your bounds and you have separable integrands. So not every function of x, y, and z could be written like this. But maybe after you've split up one of these, you can. combining all these ideas together could save you a ton of time. So I think the rest of what I had planned today was just a couple of examples using odd symmetry. The integral of a sum is the sum of the integrals, known volumes, as well as just all numbers bounds, separable integrand trick. So be careful. I've seen people overuse this. It's very important that you can write this integrand as something of x times something of y times something of z. So don't do any nonsense factoring. Like if I had x plus, I don't know, like x squared plus, what would this look like? Y x. No, actually that one's fine. No, that one's not fine. You can only really factor it as x times x plus y. So, you know, I've seen people make up bad stuff like, oh, this is x squared times 1 plus y, and no, you can't make up garbage algebra like that. So just be careful that your integrand, in fact, factors. And then in addition, make sure your bounds are all numbers, because clearly, if any variables appear in any of these, it's going to be in your final answer. And remember, our answer has to be a number. So it's very important that both these things, separable integrand, all bounds, are numbers. But, I mean, the nice thing is if you use this trick when you're not supposed to, it's pretty clearly giving you something very wrong. Either you made up some bogus factoring or your answer won't be a number. So there should be alarm bells if you're at least somewhat careful. I don't think it's that dangerous. As long as you're not, basically, if you shouldn't be using this trick and you use it anyway, you're making a very big mistake. So as long as you're paying somewhat close attention, you'll catch yourself. So anyway, let's get to these examples. So calculate triple integral of 3 plus x squared plus 2z plus xy, where e is the ball, x squared plus y squared plus z squared less than or equal to 4. So let's think about our ball. It's, I guess I usually use blue to shade in my solid regions. Okay. So this ball is centered at the origin, right? And so we have x, y, z. And so it turns out, as soon as I see this, my ball is symmetric over the xy plane. So I'm on the lookout for odd and z functions. Well, I guess maybe I'll call it terms, odd z terms. But in addition, this region also is symmetric over, this is the xz plane. So therefore, odd y terms integrate to 0. And then finally, it's also symmetric over the yz plane. So odd x terms integrate to 0. Okay, so is this whole integral 0? No. Because if I change x to minus x, so this whole thing, so the whole integrand, not odd in x, since 3 plus x squared plus 2z plus minus xy is not equal to minus 3 plus x squared plus 2z plus xy. Sure, it flips the sign on the fourth term, but it doesn't flip the sign on the first 3 terms. So it's not odd in x. Similarly, it's not odd in y or z either. But it doesn't have to be for these shortcuts and these ideas to be valuable, because integrals play nice over addition and subtraction. So instead, when I see something like this, the very first thing I do is I say that, oh yeah, this is the triple integral of 3 plus the triple integral of x squared plus the triple integral of 2z plus the triple integral of xy. And now, on these individual terms, we see things that can help. So this here is odd in z. So that term integrates to 0. xy, you could use either x or y oddness because we have both yz and xz plane symmetry. Whatever, let's just use the fact that this is odd with respect to y and the fact that I have xz plane symmetry of this ball to tell me that that integrates to 0. And then finally, let's use a different color. This here, the triple integral of a constant is the constant times the volume of the region over which we're integrating. Last time I checked, we know the volume of a ball. So overall, what we've been able to do is reduce the amount of work we have to do to just 3 times the volume of that ball, so 4/3 pi radius cubed, not squared, cubed, and then plus the triple integral of x squared. So unfortunately, x squared, it's not odd with respect to anything, so we are actually going to have to do that. But what do you know? So what is this? 4 times this, so 32 pi, whatever, plus, so for this ball, 0 to 2 is the radius, 0 to 2 pi, 0 to pi, so all angles. X squared is rho cosine theta sine phi squared, and then dv is rho squared sine phi d phi d theta d rho. And what do you know? This is a separable integrand. Our bounds are all numbers. And so, I mean, it's, as far as the importance of applying this trick, I'd say it's not really a shortcut because there's 3 steps that you still have to do. So if you do it as a big triple iterated integral, you're doing the inner, then the middle, then the outer. But for example, when you're doing this phi integration, you're pretending that rho and theta and all this stuff are constant. So you're like writing stuff down without doing anything to it because they're constant factors, which means they don't disappear, they just stay there. So I find that the way my brain works is that if I have to keep writing something down without doing anything with it, I'm likely to forget about it. So the fact that if we were doing this as a 3-step iterated integral, you're not really doing anything with these rows until the very last step. I don't know, I might forget about the rows accidentally. So in that sense, I really do prefer recognizing that this integrand factors into rho to the 4th times cosine squared theta times sine cubed phi. So looking at all of it, that's how that works out. And then at this stage, I can work on each of these factors here as just, Calc 141 problems and just multiply those results together. So I don't know, it's up to you. It's literally the same amount of work. You're not really cheating your way out of anything. But for me, it just allows me to focus on the rows, focus on the theta stuff, focus on the phi stuff. And I think all of us are going to have an easier time piece by piece instead of having one big mess that you're sort of iterating. So anyway, 32 pi plus, well, this is what, 2 to the 5th over 5. That's easy. We do have to use some trig identities for this stuff. So for this, you're going to use the fact that, so for theta, cosine squared theta is 1/2 plus 1/2 cosine of 2 theta. So remember, when you have to anti-differentiate cosine squared, you do that, which means that the theta antiderivative is theta over 2 plus sine of 2 theta over 4. For phi, you're going to need to use the fact that sine cubed phi is sine phi, well, I'll write it sine squared phi times sine phi, which is 1 minus cosine squared phi times sine phi using Pythagorean theorem. So I get sine, well, yeah, if I do it like that, and then I hit it with a u equals cosine phi substitution, I get that this is minus 1 minus u squared du, because this sine phi here is minus du. And so if I go back, my antiderivative is, minus, well, u minus u cubed over 3. And so that's what we get there. Yeah, looks good. So we probably won't make you deal with sine cubed or cosine cubed in a big multi-step question like this. That's sort of a separate little trick. But sine squared, cosine squared, I'll remind you on the next slide the important details. But that's how you do these antiderivatives. And at this point, you pretty much just plug in and subtract. So 32 pi plus 32 fifths times, this works out to be pi when you plug in 2 pi 0 and subtract. And then here, what is this? Minus 1 minus 1/3. Yeah, because cosine of pi is -1, -1 cubed is -1, and then minus minus, so plus cosine of 0, so 1. Minus 1/3. So what does this end up being? 2/3 plus 2/3 is 4/3. So yeah, nothing too exciting here. Just plugging in some values. Get 4/3. Okay, and so whatever that ends up being, what, 128? Not really worth it. 32 plus 128 over 15 times pi. Anyway, that's that. So maybe on this, maybe down here, I'll show you the relevant identities. The cosine squared theta is 1/2. And this, yeah, we talked about back with polar, 1/2 cosine of 2 theta. Sine squared theta is 1/2 minus 1/2 cosine of 2 theta. But the other thing you can get used to at this point in time, if you want, So if your bounds aren't 0 to 2 pi, you have to be a little bit careful and probably go through all the steps. But this happens commonly enough that you could just remember that if you do 0 to 2 pi of either cosine squared or sine squared, you always get pi. So it's good to know these if it's not 0 to 2 pi, but you can just memorize that. That's fine. Okay, but anyway, let's do this next one. So again, all this stuff you didn't really need to do, but it really cuts down on work. So you, of course, would have gotten the same answer had you done this entire integrand in spherical coordinates. It just would have taken a lot longer, would have been a lot messier. Okay, so anyway, let's take a look at this last one. So calculate this, where E is the bottom half of a ball. So bottom half of, I think radius 2 is easier to deal with than radius 3. So it's just the bottom half of our previous region from the last example. Okay, so anyway, this one does not have symmetry over the xy plane because we don't have any part of it where z is positive. But it is still symmetric over the yz plane, and it still is symmetric over the xz plane. So anyway, I could get started the same way as last time. It's the triple integral of 5 plus the triple integral of x plus the triple integral of 2z. X is odd in x. The region is symmetric over the xz plane, so that term integrates to 0. It's a half of a ball. So this is 5 times the volume of our region E. So 1/2, 4/3, pi 2 cubed. The volume of half of a ball is just half the familiar formula that you've known for years. So plus 0 plus, this is the only term we actually have to set up. So 2z is 2 rho cosine phi. dv is rho squared sine phi, d phi, d theta, d rho. And then our bounds are 0 to 2 for rho, 0 to 2 pi for theta, and then be careful, it's the bottom half, so phi starts at pi over 2 and goes down to pi, the south pole. And so just like before, so what we get, this is 80/3 pi, 2 times, yep, looks good to me. And then we can do our good old separable integrand. Bounds are all numbers, so 0 to 2 rho cubed d rho times 0 to 2 pi of d theta times pi over 2 to pi of cosine phi sine phi. So 80/3 pi plus, well, rho to the 4th over 4 is 2 to the 4th over 4, so 4. Integral 0 to 2 pi of d theta. Be careful, there's this 1 hiding here. So the antiderivative is theta, so you end up getting 2 pi. And then finally, antiderivative of that could be sine squared phi over 2, which between pi and 0 gives you, pi over 2 and pi gives you a minus 1/2. So whatever that ends up being, 80/3 pi minus 2 pi is what, 74/3 pi. Oh no, sorry, minus 4 pi So what, 68 thirds pi. But yeah, that's the idea there. I think that's why for regions where you have a choice between spherical and cylindrical, when you have a sphere involved. So yeah, when you have a sphere involved, your bounds are for cylindrical aren't that bad, but your z bounds will include r, which means that if I were to do this in cylindrical, oh yeah, let's just for practice, cylindrical for this would have been, well, r goes from 0 to 2, theta goes 0 to 2 pi, z would have started at the bottom part of that sphere, which is given by equation z is minus the square root of 4 minus x squared minus y squared. When you sub in for r, you get that. And then the top surface is the xy plane, so 0. And then all this, so 5 plus r cosine theta plus 2z r dz d theta dr. So the reason why spherical is so much better for this is that in cylindrical, this part is fine, but your z bounds involve r, and so you miss out on being able to do that kind of trick. So anyway, when you have a sphere somewhere, use spherical, but if you don't have a sphere, don't, because you don't want to have to deal with something awful like rho is 4 secant phi for a situation where you have no sphere. But anyway, that's what I had in mind for today. So I will see you later. Have a good day.